Uh, Good morning, dear student, and welcome to this second recording or second part of the tutorial. In this tutorial, we are going to proceed with conditional expectation compared to what I said last time, that we are going to talk about Martingale. But before doing that, there's another example that I want us to solve together, which is the exercise on your screen. So you are given xi, which is a sequence of random variable, IID, that is independent and identically distributed with probability that x subject is equal to -1 is the same as the probability of x subject equal to +1, which is constant, equal to 1/2. And we denote by Sn the sum or the final sum of xj, where j runs from 1 to n. So the sequence of xn is what we commonly call a symmetric random walk. So we are going to be dealing with a symmetric random walk. So we are asked to compute the expected the conditional expectation of x1 given the sigma-algebra generated by Sn. And similarly, in the second question of the exercise, we are asked to compute the conditional expectation of Sn given the sigma-algebra generated by x1. And finally, in the third question, we are asked to compute the expected or the conditional expectation of Sn plus m squared given the sigma-algebra generated by Sn. So in order to tackle this problem, we know already that each time we talk about sigma-algebra generated by a random variable, if I have a random variable, let's say two random variables, x and y, if x and y are two random variables, each time we write the conditional expectation of x given y, it is the same thing as the conditional expectation of x given the sigma algebra generated by y. Right? So, meaning that in our case, we can, instead of working directly with the conditional expectation of x1 given sigma Sn, we can just compute the conditional expectation of x1 given Sn. So in other words, what we need to do here, we just need to compute the conditional expectation of x1 given Sn. So this is what we are going to compute. Okay, our random walk is symmetric, which means for a symmetric random walk, the expectation is of Sn is 0. Actually, we can see actually even from this definition, right? Of course, this is not important in what we are going to do, but we can still see that the expectation of Sn which in our case this by linearity, it will be the sum of all this, right? It will be sum of xi, and we know that they are IID, meaning that they have the same expectation. They have the same expectation. So if the expectation is the same, if it is the same, we can say it's the same, this is the expectation of x1. And this will give us n into x1, ex1, I mean, because we have the same expectation. So we have this result. And what did I also say that is equal to 0? We can see here that for any xi, or I could have written any of them here. The xi are actually what we also call the Bernoulli random variable. It takes two values, -1 and 1, with probability 1/2. So if we replace that here, this will give us n into, now if I compute for x1, that can be any of them. Each one of them take two values, right? So we know already the definition of expectation. So the value taken by xi times the corresponding probability. So since there are two values, the first value, if it is -1, the probability is p, and when it is 1, the probability is also p. So that will be p minus p, or -p plus p. That gives us exactly 0, right? And each one actually, this is 0 for any of them. So the symmetric conditional expectation of the symmetric random variable is 0. Okay, that was just a parenthesis which will not influence completely what we're going to do. So an important property each time that we condition, so for any ij, if I condition xi respect to Sn being this symmetric random variable, it will be exactly equal to conditional expectation of xj given Sn. So we obtain this equality due to the fact that we condition with respect to Sn. So this is true. This is by symmetry. And what is the consequence of this? The consequence of this is that what I wrote above, okay, no, this was not condition. This was not condition. If I take, for instance, this x1, this one given Sn, meaning if I take an arbitrary, if I fix, for instance, I equal to 1, it will be for any j here. if I sum this, right? So actually, since it's true for any ij, I can say that this is equal to conditional expectation of x1 given Sn. So I can say this. Now, if I sum this from 1 to n, this is constant. It will be n this, so it does. If I sum here, n, conditional expectation of x1 given Sn will be equal to, now I use the linearity, okay, that is, I see I sum on both sides. I can take this to the conditional expectation of xj given Sn. So by linearity of the conditional expectation, this summation will go inside here and give us, so if you take the sum inside, we have conditional expectation of Sn given Sn, right? And this is Sn. Why is it equal to Sn? Is Sn, that's just simple to see. We say that this is constant, right? Because we see it doesn't depend on I or j. It's the same value all over. So if I call that constant, for instance, c, right? What we will get is that if I sum, I will have nc. nc, you can see from here that nc, if I sum here, okay, that's to find the value of c. Okay, anyway, let's see. So if I sum this, I'll have n into c. I don't know if we will bring something new, but let's go. Okay, so NC will give us NC would give us this. Will I write something? I think I'll go back to this, because if I write NC, I will sum, right? If I sum, I will get this. I'll get this back. Okay, so let's proceed. So from here, I can solve for this. So therefore, from this, we can see that expected value of x1 given Sn right? We just divide Sn by n. So that's what we get here. So, which is exactly what we are looking for, right? So that's the result. So the second question, for the second question, we are going to compute conditional expectation of Sn given S1. Actually, it's as if you are swapping these two positions. It is what it looks like. But anyway, okay, so if you use, if you use the linearity of conditional expectation, we know what this Sn is. It's a sum. It's the sum of the xi's, right? So we can split this. This is x1 plus the summation. Now in the summation here, we can start from 2. So we split the sum into 2. So this is xg. Now, if we use the linearity of the conditional expectation, we can write that the conditional expectation of Sn given S x1 is equal. So we apply on both sides, it will give us a conditional expectation of x1 given x1 plus conditional expectation of this summation, right? And we can take the sum out. Okay, let's write it first. Given x1, which is the same as the conditional expectation of x1 given x1 plus, we take the sum, linearity of conditional expectation, xj given x1. And we know that the xj's are independent of x1. Right, so that's something that we know. Since they're independent of x1, so it will be sum of xj because we don't need to write this. So this will give us And we can also see that x1 is sigma x1, or is x1 measurable. By measurability, because we condition x with respect to x1, so by measurability, this will give us exactly x1. So this will be x1. And because remember that this one is the same as conditioning by x1. So we'll get this plus, and the fact that the xj are independent of x1, it will give us the sum j running from 2 to n expectation of xg. Yeah, but we know that these are all zeros, right? Because the xj is, recall the definition. We even prove it above. Yeah, we saw that for any j, this will always give us 0. This will always give us 0 because it takes only two values, -1 and 1, with the same probability p. So if we substitute exactly as we did here, it will always give us 0. So that will always be 0. So this is 0. Right? So in other words, since they are all the same, that will be from 1 to n, we have n. From 2 to n, we have n minus 1. So this one will give us, so this will be x1 plus n minus 1 into this expression, which is 0. That is, as we saw, it will be -1 plus p. So this is 0. And the result is x1. So in other words, which is the same if you replace this with sigma. It's x1. Okay, so we are done with this one. And finally, the last one. So the last one is n plus m square given sigma Sn, which is the same as Sn. So So this is what we are going to compute. So we know that obviously this is a sum from 1 to n plus 1, so we can split this as we want, right? We can first sum from 1 to n, which will give us Sn plus okay. I think we can write this as n plus 1 minus Sn. So if you write this, actually we add and subtract Sn. And this is an increment. Okay, let's say it, let's put it that way. So we can say that this is S n plus r, where r is this quantity, right? And that quantity, if we write this in terms of summation, you can see that if I split this into two, this will be Sn plus it will be Sn plus the sum from n plus 1 up to n plus n, right? So this is the sum, because this Sn starts from 1 to n, and the remainder, that's why we call it n, the remainder, we start from the next term, which is n plus 1. So here j, we start from n plus 1, that's the next term, up to the final term, which is n plus m. N plus m of what? Of xj. Yeah, so that's what we have here in this expression. So we can say that S n plus m square, don't forget that that's what we want to compute, the square, the square. So if we write that, it will be a sum of, it will be the product. Oh, sorry, this is equal. This is equal, not plus. It's a typo. It's a, yeah. So that is equal. Now, if I use this notation, it will be Sn squared plus 2 Sn times r plus r squared. Okay, so that's what this will give us. We just multiply this by itself, or we square this. We use this identity. Now, but something that we need to see is that r is independent of Sn. R is independent of Sn. So we're going to see here that since R is independent of Sn and due to the fact that the expectation of R is 0, right? We know that by linearity, if we compute the expectation of R, will be the sum of the expectation of xj, and we know that expectation of xj is 0. So this is for any j, this is 0. Now we're going to use the property of the conditional expectation. The conditional expectation of this 2S and R, you see that 2S and R given Sn so this will give us to Sn, we take out what is known. This is known because it is sigma Sn or sigma Sn. This is known. Sn will be known, right? So this will be 2 Sn and then conditional expectation of R given Sn, but from what we stated here, R is independent of Sn, therefore this conditional expectation is just the expectation of R, right? So, and that is 0. So this will be 2 Sn expectation of R from this, so that expectation of R is 0, so this is 0. Okay, so what is left here? So we have already expectation of this, of course, because we are going to take the conditional expectation, right, of x squared given s. Since it's linear, we will compute each one. So we have seen that this is 0. We are going to compute this one, meaning that by linearity, this given Sn will be expectation of Sn squared given Sn plus expectation of R squared given Sn. So let's compute. Okay, so if we take R squared, if we compute sorry. Okay, sorry. If you compute this expectation we know already that actually this will be what? This is expectation of R minus E R square. Because ER is 0, right? So if you write this, it's nothing else than what? The variance of R. So that's the variance of R. We know what R represents. This is R. Because these are independent, for independent random variables. So if I take the sum of independent random variable, the variance will just be the sum. And we have a total of how many sum? So this will give us sum J from n plus 1 to n plus m variance of xg. But you see that we have m here, we have m there. So the total number here will be m, right? Because we start from n plus 1 up to n plus n, right? So if we have n here, so it's as if we are summing from 1 to m, the total will be m. So this will be m times the variance of xg. But we know that they have the same, they all have the same variance, which is 1. So this is times 1, which is m. So the variance of R is m, right? So now if you substitute this expression, this expression of S n plus m squared, and we perform the conditional expectation, we use the linearity of the conditional expectation, right? We will be left with the conditional expectation of this given Sn and this given Sn, which is exactly this m. So hence, the conditional expectation of S n plus m square given sigma Sn, which is Sn actually is the same, right? This will give us it will give us Sn square. Why Sn square? Let me write it properly here. They give us, we will have this Sn square given Sn plus m. But this one, this one is actually Sn square itself. Why? Because I can write that in many ways. Huh? I can say that because this is as if I'm writing conditional expectation of Sn times Sn given sigma Sn, right? I can take this out, because Sn is known. I cannot take both, otherwise I will be left here with one. It's not interesting, so I consider this is Sn into Sn, sigma Sn, which I can see right Sn here. But we know that this is still Sn, right? So, which will give us Sn squared. So it is as if anyway, so they give us Sn squared plus m. So yeah, so that's the conclusion. So we conclude here that the conditional expectation of S given Sn is equal to Sn squared plus n. In other words, what does that show us? If I take this inside here, because this is deterministic, so I can take it inside. And this, which is, I mean, this conditional expectation is the same as conditional with respect to sigma s n. So if you take f sub n to be the sigma algebra generated by x1 up to s n, it is the same sigma algebra generated by Sn, right? Which actually, I cannot say that this sigma algebra is equal to Sn, but I mean that I hope you see where I'm going. So, meaning that I can rewrite this expression here as S n, I mean m plus n squared minus m given Fn, right, which is this sigma algebra here. This one, which is still the same as if a condition with respect to Sn. We see that it will give us what? Oh, okay, anyway, something like this. Okay, but it's not what I was expecting. Okay, so okay, so that's the end for this part. I will stop here and we will move to the next one, the last one, in the next few minutes. That's where we are going to talk about Martingale, right? Because so far we are talking about conditional expectation, we're going to talk about Martingale. So thank you for your kind attention. God bless you and see you in the next tutorial.